Hi everyone, welcome to our sixth lesson in the limits unit, and this lesson is about continuity. So I'd like you to just pause the video for a minute and see if you can list some different ways in which a graph can be discontinuous. Discontinuous or not continuous means a graph has a break in it in some way. You have to lift your pencil as you draw the graph. So pause the video and see if you can list some ways that you've already seen and that we know about when a graph can be discontinuous. So hopefully you came up with the, following examples. You might have written a hole, right? A hole is a way for a graph to be discontinuous because here's a continuous graph and then I have to lift my pencil because at this particular x value, x is equal to a, there's no y value, and that's what the hole means. That's a discontinuity. That's a way to be not continuous. A vertical asymptote is another way that a graph can be discontinuous. So you have to lift your pencil on the other to get to the other side of the vertical asymptote. And you can maybe even think of a piecewise function that could have a discontinuity, right? So these are the basic ways in which a graph can be discontinuous. And in calculus, we look at these different ways in terms of limits, right? So the first reason why a graph might be discontinuous, this is what causes a jump in the graph, is when the left limit does not equal the right limit. So here we're talking about this place, x is equal to -1. And at that spot, we can see that the limit of this function as x approaches 1 from the left down here is equal to -1, but the limit of f as x approaches 1 from the right, which would be up here, is +1. And so since the two limits, the left-sided limit and the right-sided limit, are not equal, that creates a jump in the graph, that creates a discontinuity. A vertical asymptote, we talked a lot about that in our last class. Vertical asymptote remember the definition of a vertical asymptote is simply that the limit of the function as x approaches, in this case 2, in both of these graphs, 2, from the right, or from the left. So this is in the first graph. In this graph, we can see that either from the right or the left, we go off to positive infinity, and so that creates a vertical asymptote. Now we know that this needs to be happening only from one side for it to be already called a vertical asymptote, right? And we also know that it can be that we go off to positive infinity on one side and negative infinity on the other side, and that is also going to create a vertical asymptote. So what's happening in all of these cases is that there is an infinite limit. In other words, when we say that the limit of f as x approaches 2, say from the right, is infinity, remember that infinity really means that the limit does not exist, right? As you get closer and closer to 2, this statement says that the y number keeps on getting bigger and bigger and bigger, right? It grows without bound, is what we're saying, right? So when that happens, that's going to create a vertical asymptote, which is going to be another discontinuity. A third type of discontinuity is called an oscillating limit, and this is a graph of the function sine of 1 over x, right? And so you can already see that x is equal to 0 is not in the domain of this function, right? So you cannot get a y value for x is equal to 0. If you were to zoom into here, what you would find in this function is that the graph is oscillating faster and faster and faster between -1 and 1, right? And as you get closer and closer to the y-axis from either side, these oscillations just get more and more quick, right? And they just never end. And that's called an oscillating limit. Remember that a limit means that the y value actually settles down towards some number. In this case, you can see that it's not settling down at all. It's jumping between -1 and 1 and all the values in between, no matter how close you get to the arrow number, right? So we would say here the limit of this function as x approaches 0, we could say from the right or the left or overall, is a DNE because the function just doesn't settle down. And that's another way in which we can have a discontinuity in a function. Okay, and that's called an oscillating discontinuity. And the last and perhaps the most familiar way in which a function can have a discontinuity is when we have a hole, right? And in a hole situation, what's happening is that the limit of this function as x approaches 1 exists, right? It's equal to 2, but the function value at that arrow number, right? In this case, it's a DNE, and that creates a hole. It could also be that the function is defined at, say, 4, right? But these two numbers, the limit value and the function value, are not the same, right? That's what creates a hole. Okay, so basically all these are the four types of discontinuities. They're called the jump discontinuity, an infinite. So this, let's write these down. This is a jump discontinuity. This is an infinite discontinuity. This one is called an oscillating discontinuity. And this last one here is called it's really called a removable discontinuity, right? And that brings me to the point that's important to remember, that out of these discontinuities, these four, the only one that we can remove, right, is a hole. And the way we remove that is going to be something I show you in a minute. But let's first write down what we mean now by continuity, right, from these observations. What can we say about continuity at a specific point, right? And by a point, I mean at x is equal to a. So f of x is continuous at x is equal to a if, right, and IFF means if and only if, right? Three things happen. First of all, the first thing that has to happen for a function to be continuous at a particular x value is that f of a is defined, right? Which means that a is in the domain of f. Secondly, the limit of f of x as x approaches a has to exist. And third, the limit of f of x as x approaches a has to equal f of a. If these three things happen, then the function will be defined at the point x is equal to a. I'll come back to this side of the box in a minute, right? So a fun fact is that, remember, we found that in a couple lessons ago, if you had a function where you wanted to find a limit, and you could just plug the arrow number in. That was always our first way of trying to find a limit. And then some functions this would work, and then in other functions it might not work, right? We saw this in many different problems. The reason this direct substitution works, when it works, it's working because the function is continuous at the arrow number, right? You can see that this function right here is continuous at x is equal to 1. This function right here is not continuous at x is equal to 1, right? So that's why direct substitution works, okay? Let's move on now to using the three-part definition of continuity to test if the function is continuous at the given value, right? So you can look at these problems like this one, f of x is equal to x squared minus x minus 2 over x minus 2. You can immediately see this is a rational function. We know from pre-calc that rational functions have holes and they might have asymptotes, might have holes, might have asymptotes, therefore they might be discontinuous. We can just from pre-calc figure out that this right here has a hole, right, at x is equal to 2, and it has no asymptotes. Okay, so this the fact that we're discontinuous at x is equal to 2, that we can figure out from pre-calc. But in calc, we want to be able to say this very precisely using the three-part definition of continuity. So we want to be able to say something like f of, you're going to write three statements. F of 2 equals a DNE. Actually, in this case, you don't even need to write three statements, because the very first condition that the function is defined does not work. In other words, 2 is not in the domain, right? That was our first condition for continuity. So you can just say f of 2 is equal to DNE, therefore f of x is not continuous at x is equal to 2. Okay, let's take a look at the next one. The next one is a piecewise function, and I want to mention to you that when you see piecewise functions, get in the habit of recognizing this type of piecewise function, okay, versus, I'll write another one. Another function might look like something like this, right? Okay, this right here, you can see when you have the greater than and less than signs that are separating the breakpoints, this is going to possibly be a jump, okay? But this right here, it's the same rule for all x not equal to 0, right? So this right here is going to be a whole. So possibly a whole, right? So when you see these two types of piecewise functions with the equals here versus the greater than, less than, just recognize that there are two types of piecewise functions. This one right here, we might possibly have a whole, but let's check if we actually do, right? Okay, so how do we check? Well, we use the three-part definition of continuity. Does f of 0 exist? Well, f of 0 is equal to 1. So that does exist. Now let's check if the limit of f of x as x approaches 0 exists or not. Well, this is a piecewise function, so we have to be careful to check from the right and from the left. In this particular piecewise function, the rule is the same coming in from the right or the left. And in both cases, we can see that we basically have a vertical asymptote, right? Here, because you cannot put in 0 into that, so direct substitution doesn't work. And as x comes in from the right, you having this situation, and as x comes in from the left to 0, you're having this situation. So we've got a vertical asymptote situation, which is clearly a discontinuity. The limit doesn't exist. Remember that infinity in any case is really a DNE. So since the limit doesn't exist, you can just say the limit of f of x as x goes to 0 equals DNE, therefore f of x is not continuous, right? So again, we are showing our reasoning based on the three-part definition. Okay, continuity on an interval. So this was continuity at a point. Continuity at an interval means f of x has to be continuous at every point in the interval, right? So let's take a look at what that means. I want to show you 4 pictures just to make this kind of, it's a little bit obscure concept, but it does come in handy to understand this. So you can look at this first picture and realize that in this case, f of x is continuous on the interval, we would say AB, right? And I've put parentheses on here because we're not continuous over here and over here. You can clearly see there's 2 holes there, we're not continuous. Okay, let's take a look at another picture. This picture might look like this, right? And here you have a hole only on one side, right? And so we would say we're continuous on bracket A parentheses B, right? Let's do another one. Here, let's be continuous on the right side, but not on the left side. So, right, so here we're continuous on A, parentheses A, bracket B. And then the last one would be something like this. And here we're continuous on bracket A, bracket B, right? So this, you can have all these 4 cases when you're looking at an interval of x values. And we can use, for example, this picture here to think about what we mean when we talk about one-sided continuity, right? So one-sided continuity is what's happening in this picture, right? So because we don't know what the function is doing to the left of a, right? We don't know. That part is not even shown in the picture. But we know that the function is continuous at x is equal to a, but it's continuous only from one side, right? And what we mean by that is that f of a exists, it's this dot, whatever that value is. The limit of f of x as x approaches a exists from one side, right? So this exists from one side. And we can see that it's equal to whatever this f value is. The limit is also equal to that value, whatever it is. Say it's 2, then the limit of f from the right side is 2. The two values, f of a and the limit, are equal. And so when we can make that kind of statement from one side, in this case from the right side, then this function is continuous. We say this function is continuous at x is equal to a from the right side, right? That would be what one-sided continuity means, right? This function, for example, here, f is continuous at b from the left side, right? So that's what we mean by one-sided continuity, and we can go back and put these words into the box on page 1 where I filled in the two-sided continuity, right? You want to fill in the one-sided continuity. This one is one-sided continuity from the right, and you can make a similar list of 3 conditions for one-sided continuity from the left. Okay. So now, functions that are continuous for all numbers in their domains, we know a lot of them: linear, quadratic, polynomials, rational trig, inverse trig, log, and exponential. Functions which may not be continuous on their domains are piecewise functions and absolute value functions, right? So recognize, clearly, for example, the rational functions which have wholes and asymptotes, or the trig functions which have lots of asymptotes, those are not continuous everywhere. They're just continuous for the numbers in their domain, right? Which means that, for example, tangent function is obviously not continuous at pi over 2, but everywhere else it's continuous. These functions, the piecewise and the absolute functions, right, they might actually be discontinuous even within their domains, right? So this is the distinction between the two types. And we're going to look a lot at these two types, piecewise and absolute, in this first unit, because precisely because they are not continuous often, and so they give us a chance to practice all our different limit skills that we're learning here. Okay, so example 2 says, on what intervals are the functions below continuous? Use interval notation to answer, right? So you do these problems mainly using pre-calc skills, I would say. This one has a vertical asymptote at x is equal to 2. So then that means you can see that it's a transformation of a over x minus h plus k. It's one of those rational functions. You're going to have a horizontal asymptote at y is equal to k and a vertical asymptote at x is equal to h. And so we're going to be continuous on the interval. So continuous on, we would say, negative infinity all the way to negative 2, not including negative 2, because that's where we have the vertical asymptote, union negative 2 to infinity, right? So just a statement about where is this function continuous. This guy, you're going to factor. It's a rational function. You're going to have to factor to figure out the asymptotes or wholes. You're going to notice that we have a vertical asymptote at x is equal to 3 and at x is equal to 1. And so we can say that we're continuous on negative infinity to 1, union 1 to 3, union 3 to infinity, right? You're always going to think of the lesser one, of course, is here, and the greater one is here, right? So the function is continuous all the way from here to here. It's not continuous at 1. We have a vertical asymptote there and a vertical asymptote here, right? So we want to precisely, list all these different places using interval notation. So I'm trying to color code here to show you the the lining up of the words with what, I mean, of the interval notation with what's happening on the graph. Okay, we talked about hole discontinuities and how the holes are removable. They're the only type of discontinuity that we call removable. And what we mean by that is, if you're allowed to reassign the x value at the place where the hole is, what would you make it so that the discontinuity goes away, right? So for this example, it says let f of x be this function. They've excluded 1 and -1 because clearly those are the excluded values for this domain. And then they're saying assign a value to f of 1 so that it will be continuous at x is equal to 1, or explain why this is not possible. So you first have to look at that function and recognize you got to be able to factor the top. And I keep saying, please be really good at factoring. Let's just review here. 2x squared minus x minus 1. We need two numbers that multiply to -2 and add to -1. Those two numbers would be -2 and 1. And now you have to break up this central term into -2x plus x. And then factor by grouping. So then you go 2x times x minus 1 plus 1 times x minus 1. So my two factors are 2x plus 1 and x minus 1, right? So this becomes 2x plus 1 times x minus 1. On the bottom, I have x minus 1, x plus 1 by a difference of 2 squares. So I have a hole at x is equal to 1 and a vertical asymptote at x is equal to -1, right? So I have to think through that before I actually try to do the problem. And now, because I have a hole at x is equal to 1, let's think about it now from a calculus standpoint, right? So right now, f is not continuous. At x is equal to 1, you have a hole, right? So let's think about what that means in terms of our three-part definition of continuity. So right now, f of 1 is a DNE. The limit of f of x as x approaches 1 is equal to, well, you are going to do exactly what we did above with the factoring, and you're going to be at this spot, and then you're going to be able to put in the 1, and you get 3 on top and 2 on the bottom, right? So we've got a situation where the function value doesn't exist, the limit value exists, right? So if f of 1 is assigned to be 3/2, right? If you make it, if you force it, right, then we would have that the limit of f of x as x approaches 1 is equal to f of 1, and f will be continuous at x is equal to 1. So we can, in fact, make f continuous at 1 by making f of 1 equal to 3/2. Let's take a look at -1. So at -1, what we have is a vertical asymptote, right? We know that a vertical asymptote is an infinite discontinuity, and that cannot be removed. So you could just say that. You could say f of x has an infinite discontinuity at x is equal to -1, and this is not removable. Okay, so that's holes. Let's talk a little bit about jump discontinuities. So here's a piecewise function, and we actually looked at this piecewise function a few lectures ago, and you can pause the video and make sure you know how to graph this, which you should be able to do, but I'm going to just quickly graph it here again. This particular piecewise function looks like this, and we're going to examine, actually you should just pause the video and make sure you can answer all the limit questions about this piecewise function that are right here, right? This is a review problem. So you can tell that as we approach -1 from the left side, the limit is 0. As we approach -1 from the right side, the limit is 1. Overall, there's no limit at -1. At +1, the limit from both sides is 1. And so the overall limit is 1. Okay, so that's the review of piecewise functions. Now, sometimes a piecewise function, actually you can see it in this one. Here, this piecewise function is discontinuous, right? and here this piecewise function is continuous. So both things can happen, and how do we check whether a piecewise function is discontinuous or continuous at the break point, right? Well, one way would be to graph it, but you have to be sure you graph it correctly. Another way is to use the three-part definition of continuity, and that's what we're going to need to do in calculus, right? So let's check the three-part definition of continuity here in example 5. So first thing is we're being asked at x is equal to 4. So g of 4, does it exist? Well, this is the rule that I need to use for that. So I go 4 squared minus 4, or 12. So g of 4 does exist. Check on that. Let's check whether the limit of g as x approaches 4 exists, right? And this being a piecewise function, that then leads me to check what the limit is as I approach from the right, and what is it when I approach from the left. So this greater than 4 is approaching from the right, and less than 4 is approaching from the left. So that means that for approaching from the right, I'm going to use this rule, and I'll get an answer 4 times 5, or 5 times 4, 20 minus 6 is 14. From the left, I'm going to use this rule, and I get 16 minus 4, or 12, right? So the two limits are not equal. The overall limit is a D and E, right? And that's what you need to show. Once you show that, you can say, so g of x is not continuous at x is equal to 4. Continuous at x is equal to 4. That's an answer based on the three-part definition of continuity. Let's check out another couple examples here, right? So this one, example 6, says, let f of x be the function defined below for what value of k is f continuous at x is equal to 3. So a few things. First of all, you can see this piecewise function is the one that might have a hole. It's not a jump type of a piecewise function. Second of all, you can see that the function value at x is equal to 3 has been left undefined. K here means you can decide. It's a variable, right? You can decide what k is. That's what they're trying to say with this problem. And they're saying, what value would you choose if you wanted this function to be continuous, right? So clearly we know that it's going back to the three-part definition. Right now, f of 3 is equal to k, right? And we need to figure out what is the limit of f of x as x approaches 3, and then we'll be able to make k equal to that. And if we do that, we'll have a continuous function, right? So let's check out the limit of f of x as x approaches 3. From the right and from the left, it's the same rule in this case, right? It's the same rule right here. X is not equal to 3 means basically you can't use that rule for 3, but from the right and from the left of 3, it's that same rule. So we're going to use that and see what happens. I'm going to factor as I go. Actually, let me just factor the top immediately into difference of two squares. Direct substitution doesn't work, by the way. You can check that for yourself. And so now I get 6 divided by 3, or 2. So the limit as x approaches 3 is equal to 2. So if k is equal to 2, right, if the function value is also equal to 2, then the limit of f of x as x approaches 3 will be equal to f of 3. Both of those will be equal to 2, and the function will be continuous at x is equal to 3. That's how we answered that question. Okay, this one is a similar problem, but in this problem, notice we have this other type of piecewise function where the issue is a jump, right? It's not a hole, it's a jump. And notice also that you've been given this variable c that you can choose, right? In this type of problem, there's going to be a variable that you can choose. So we know that a jump, the problem is going to be the left and the right limits not lining up, right? So First, let's just do it systematically though. Let's do f of 2 right now. F of 2 is going to be 2 cubed minus 2c. That's 8 minus 2c, okay? The limit of f of x as x approaches 2 from the right, that's going to be the same. It's going to be 8 minus 2c because we're going to put in our number 2 into the blue rule, okay? Let's now do from the left. The limit of f of x as x approaches 2 from the left, that's going to be this rule, okay? And that's going to be 4c plus 2c, or 6c, right? So I need this 8 minus 2c and this 6c to be equal for there to be an overall limit. So I'll say 8 minus 2c equals 6c, 8c equals 8, c is equal to 1, right? That will then give me that the overall limit, if c is equal to 1, then the limit of f of x as x approaches, what is it, 2, will be equal to, I can use now either equation with c equals 1, and I'll get that that limit is equal to 6. I can also go back to my first checking here of f of 2 and make sure f of 2 is 8 minus 2 times 1 now. That'll be 6. So since the limit of f of x as x approaches 2 is equal to f of 2, f of x is continuous at x is equal to 2 when c is equal to 1, right? So in this problem, the strategy was to find the left and right limits, set them equal, and assign the variable accordingly. Okay, our last topic here is absolute value functions. Absolute value functions are going to be, well, let me just remind you that the basic absolute value function looks like this, right? And this function is continuous everywhere because it is actually continuous right here. The limit from both sides is 0. The function, let's just make sure everybody understands, the limit is 0 from both sides. The function value f of 0 is 0, right? The two are the same. There's no discontinuity. I can just not pick up my pencil as I draw this graph, right? So absolute value of x is a continuous function everywhere. Absolute value of x over x, this is another important function. Okay, so this function looks like a step. At x is equal to less than 0, this function is negative 1. And for x greater than 0, this function is positive 1, right? So this function, both of these two functions can be written as piecewise functions. So let me remind you that absolute value of x can be also written as the function which is equal to x if x is greater than 0, and negative x if x is less than 0. That just means on this graph, if x is greater than 0, right, the line is y is equal to x. If x is less than 0, the line is y is equal to negative x, right? This one here, this graph, if x is greater than 0, y is equal to 1, and if x is less than 0, y is equal to negative 1, right? So you can see that this as well can be written as a piecewise function. So this guy can be written as f is equal to 1 if x is greater than 0 and negative 1 if x is less than 0. Okay, so we're going to first of all realize that since they are sort of related to piecewise functions, functions having absolute value can create jumps or can have jumps in them. So let's see if we can figure out some absolute value limits, and the strategy is basically going to be to think of them as piecewise functions. So first of all, some of them you don't have to really think about it as a piecewise function because you can think of it as a transformation. This one, the limit of the absolute value of x plus 3 as x goes to negative 3. I would say two ways to think about it. One is graphically, and just realize that this is just an absolute value function that's been shifted 3 to the left, right? And so that as x approaches negative 3 from the graph, you can immediately tell that the answer is 0. You can also do direct substitution because notice that you can put in negative 3 in here, right? So if I just do my first strategy for limits and I go negative 3 plus 3, I get the absolute value of 0, which is 0, okay? Now, the limit, I put this in here to show you that the same function, I could ask a different question, right? I could have this same function, but I could be asking you what's the limit as x approaches 0, right? In which case, from the graph, you can clearly see that it's 3. And if you put in the number in here, put in the arrow number, you're going to get out 3, right? So be careful, an absolute value function is not always asking about this vertex point, right? It could be asking about anywhere on the absolute value function. This guy, x plus 3 over x, absolute value x plus 3 over x plus 3, this is this function shifted over. This is the function that we just talked about, shifted over left negative 3, right? So, or left 3. So the function looks like this. Okay, now this one, if you do direct substitution, you're going to get into a problem. You're going to see that you cannot put in negative 3 because you'll get a 0 in the denominator, right? But you can think of this either graphically, or you can realize that this is like asking this function, right, can be rewritten, just the function can be rewritten as 1 for x is greater than negative 3 and negative 1 for x is less than negative 3. And so from that, if you're looking for the limit as x comes to negative 3 from the positive side, right, then the answer is going to be 1, okay, which you can see from the graph as well. X coming to negative 3 or approaching negative 3 from the left, right, that one, this is going to be equal to negative 1, and overall we're going to have a DNE, okay? So we can think about it that way. 3 minus x, again, this can be thought of in terms of transformations. You can remember that when you put in negative x into a function, so f of negative x is going to reflect f of x across the y-axis. So you can think like that and realize that this function is really going to look like the one above, except it's going to be reflected around the y-axis. Okay, let's talk about an algebraic way to do that problem. I'll go over here. So we're talking about the limit of 3 minus x over 3 minus x as x approaches 3, right, from the right, for example. You want to remember that you can write these kind of functions as piecewise functions, right? So the goal is going to be to think about this absolute value and to realize that if you have a positive number inside here, then the answer to an absolute value number is, the absolute value is just a positive number. If you have a negative number in here, then you have to do minus of that number, right? So we're going to take this 3 minus x and think about it. And you know, you can just think, well, 3 minus x is going to be positive if x is less than 3, right? That kind of makes sense. You can also solve the inequality and get to that. 3 minus x is less than 0 when x is greater than 3, right? And again, if you solve this little inequality correctly, you will come out with that answer, right? X greater than 3 means 3 minus x less than 0. X less than 3 means 3 minus x greater than 0. So then when x is less than 3, 3 minus x is greater than 0. So the absolute value of 3 minus x is just the same as itself, right? Because whatever you put in here is positive. So what comes out is positive. Here, what you're putting in is negative, right? So if you're doing 3 minus x in the case where x is greater than 3, then this thing is negative, and the answer you're getting is negative 3 minus x, which is x minus 3, okay? So with this, you can rewrite this whole function as 3 minus x when x is greater than 3, sorry, when x is less than 3, and x minus 3 when x is greater than 3, okay? Notice x is equal to 3 is not in the domain. So now with that, we can answer all the problems, right? When we're approaching 3 from the right side, then we're going to use this equation, right? This equation, and let's see how that goes. So then this will become limit x goes to 3 from the right of x minus 3 over 3 minus x. So this is going to be the limit of negative 1, which is equal to negative 1, right? Similarly, from the other side, from the left side, less than 3 side, there this will just become the limit of 3 minus x over 3 minus x, which is equal to 1. Okay, so from the two sides, it's negative 1 and 1, and overall, it'll be a DNE. So this guy is, I think I meant to say plus here. So this guy is negative 1, this guy is 1, and this guy is a DNE. Okay. Okay, now, so that's kind of your strategy. You're always taking the function and trying to rewrite it as a piecewise function. So this function right here, let's try to see if we can rewrite that as a piecewise function. So notice the arrow number is 0, right? So we're thinking of cases, in any case, the absolute value, the case is when x is greater than 0, x is less than 0, right? So when x is greater than 0, the absolute value of x is just x. So I get 4x over x, which is equal to 4, right? So this function becomes 4 when x is greater than 0. When x is less than 0, I get 3x minus x, which is 2x over x, which is equal to 2, right? So this function is 4 for x greater than 0, 2 for x less than 0. So that means here it's just, it's just flat lines. If you were to graph this, this function looks like 4 for x greater than 0 and 2 for x less than 0. That's what the function looks like. So if I'm approaching 0 from the left, the answer is 2. 0 from the right, the answer is 4. And overall, it's a DNE. Okay. Let's take a look at something like this. Again, same strategy. 2 over x minus 2 over absolute value of x. Well, if x is greater than 0, this looks like 2 over x minus 2 over x, which is 0. If x is less than 0, this looks like 2 over, if x is less than 0, this looks like 2 over x minus 2 over negative x, right? Which is 2 over x plus 2 over x, which is 4 over x. And so this guy, there's a very different situation from the left side, right? So that means approaching 0 from the left side, I have a situation where on top I have 4 and on the bottom I have a small negative number, so I'll get negative infinity. Approaching 0 from the right side, well, it's just this flat function at 0, and overall is a DNE. Okay, yeah, this function right here, it ends up looking something like this, I think. It's going off like that on one side, and on the other side, 0 will not be in the domain, but it'll look something like that, right, for this function. So, by the way, you can always use Desmos as well to confirm your answers or to get insight into the problems. I just did that to verify my answer here. But you want to know how to do these algebraically. You want to know how to do these problems by writing a piecewise function. That's the steps that I'm going to be looking for on your tests. Okay, let's move on to the last slide, which is the takeaways. Try to pause the video and write down these. But the three-part definition of continuity is that the function at x is equal to a, we should say, is that f of a is defined, right? The limit of f of x as x goes to a exists, and the two are equal. That's when a function is continuous. That's what makes a function continuous at a point x is equal to a. A function is continuous on an interval if it is continuous at every single point on that interval. The four types of discontinuities are the removable, which is informally we call it a hole, the jump discontinuity, right? The infinite discontinuity, which is a vertical asymptote, not infinity, I'm sorry, infinite, okay? And the last one is the oscillating. These are the four types of discontinuities. The only one that is removable is a removable discontinuity or a hole, right? We can connect piecewise functions by setting the left, or let's call it the one-sided limits at the breakpoints equal. And limits of absolute functions are found by, absolute value functions are found by rewriting the absolute value function as a piecewise function. Okay, so that's our lesson on continuity, and I hope you enjoyed and understood that.